So I'm going to ask you guys to start off with just a warm-up exercise, which is to prove the thing that we left off last time, which was that if you have some sequence Sn converging to S, and then so these are complex numbers. And you have some other constant, then when you multiply the sequence by the constant, then that converges to the limit times that constant. Okay, so this is just to sort of check that you understand the definitions. Oh, I can run back to my office and get your. Okay, so let's talk about it, right? So let's just start off by saying what we have. So right, what you have is that Sn converges to S, right? What does that mean? Somebody just tell me, what does that mean? Just rattle it off. It means that for all epsilon greater than 0.
Number in the sequence.
There exists an n?
Yeah, a map from the number so that the distance between the limit point and the sequence is less than epsilon.
Epsilon, whenever you're past that point.
Yeah.
Okay. So that's it. That should just come right out of you, like 1 plus 1 equals 2. Okay. Right. For all epsilon greater than 0, there's a time such that the distance between these points and the limit is smaller than epsilon for everything past that point. Right. Okay. Right. So that's what you have. Right. And what you want to show is basically the same sort of thing. That for all epsilon greater than 0, there exists an n such that CSn minus CS is smaller than epsilon. Right. For all n greater than n. So, right, so how do we do it? Right? We know that we can find, whatever epsilon we're given, we can find a time past which these guys are within that epsilon, these guys are within that epsilon of S. We want to show that, if somebody gives us an epsilon, we can make these guys within epsilon of each other. Okay? So, right, well, what's the relation between what we have control over and what we want to have control over? Sure.
You can factor out C.
You can factor out the C, right? So, right, you say, well, look, so some scratch work. You say, well, look, this thing is just absolute value of C times Sn minus S, right? So we want to make this thing, right? So we want this thing to be smaller than epsilon, right? Right? We want this thing to be smaller than epsilon. So that's the same thing as saying that we want this thing to be smaller than epsilon over modulus C, right? Right? So that's the same thing as saying that we want this thing to be smaller than epsilon over modulus C. Right? I guess we do have to say, like, if C is 0, then this is obvious, right? So, right. So we have to bake it into cases. So notice that if C is 0, then trivial. So assume C is non-zero, so that we can divide over here. Okay. So just to be proper. Okay. Right. So we want, what do we need? We need an n, right? We need a time past which this is true, and we can find such a time because we know that this thing goes, this thing goes to 0, right? So, right, since Sn converges to S, we know that there exists a time past which, you know, Sn minus S is smaller than epsilon over absolute value of C. Because we knew it was true we could do that for every epsilon, right? We can do that for any number, so we'll do it for this number, epsilon over modulus C, right? And so we're done. So we have it, right? That's the n we need. Right? Somebody gives you an epsilon, right? Somebody gives you an epsilon, you divide it by modulus C, and then you get the n for it from this convergence, right? And that's it. Okay. Okay. I hope that's all right. Any questions? Any questions? Okay. Okay, so today we're going to do a bunch of sort of like common, we're going to start off with a bunch of what Rudin calls common sequences. They're pretty illustrative. So yeah, let me start off with a clean board. Okay, so yeah, actually, let me start off with a sort of just like a remark or an exercise that I'll leave for you to do. Exercise. Call it the squeeze theorem. Squeeze theorem or pinching theorem, right? So you have two sequences. So you have two sequences, x sub n and s sub n, that are both sequences in R. Okay. And you guys probably know. What does the squeeze theorem tell you? You guys remember the squeeze theorem? No? And?
Isn't it if you have like two, I mean, I learned it in calculus with functions, but it's
Yeah.
like if you have
Yeah.
two functions and there's and they converge to something, and you can put a function in the middle of it,
Yeah.
then it converges to that same thing.
Yeah, exactly. So if you have two functions, and those guys, and one is always bigger than the other. Okay. And the two of them converge, have an equal limit at some point. If there's a third function that lies between those guys, then it also is forced to converge to that limit as well. Okay, so that's kind of intuitive. So there's a sequence analog of that. We'll just do a very simple one where the lower sequence is actually just the zero sequence. Okay, and then the upper sequence goes down to zero, right? And then so you've got a third sequence that's trapped between. It will also have to go to zero. Okay. So if x sub n is smaller than s sub n and bigger than zero, and 2, the upper guy goes to zero, then the middle guy must also go to zero. So that you should try that. It's not too hard as an exercise. Okay, and then the second thing I'm going to remark is the so-called binomial theorem, which tells you about how things like 1 plus x to the n. So where n is some natural number, 1 plus x to the n has a kind of nice form, which is n choose k x to the k as k goes from 0 to n. where n choose k is n factorial over k factorial over n minus k factorial. It's the number of ways you can choose k objects from a set of n objects. Okay, you've got n different objects. How many different ways can you choose k objects from it? Okay, so let me just, if I say like 3 choose 0, that's going to be 3 factorial over 0 factorial times 3 factorial, right, which is just 1. Right, 3 choose 1 is going to be 3 factorial over 1 factorial over 2 factorial, right, which is 3. Right, 3 choose 2 is going to be 3 factorial over 2 factorial over 1 factorial, which is 3. 3 choose 3 is 3 factorial over 3 factorial times 0 factorial, which is 1 again. You may recognize this 1, 3, 3, 1, right? 1, 3, 3, 1. What does that remind you of?
Pascal's triangle.
Pascal's triangle, right? And that's basically what this is saying, right? What this is saying is that the coefficients for the nth row of Pascal's triangle are those numbers in Pascal's triangle. Are these numbers? Okay, right? Pascal's triangle, right? Right, if we take 1 plus x cubed, right, 1 plus x cubed, that's, right, so, so like 1 plus x cubed, the binomial theorem says that that's going to be 3 choose 0 x to the 0 plus 3 choose 1 x to the 1 plus 3 choose 2 x squared plus 3 choose 3 x cubed. Right, which is, as we just saw, 1 x to the 0 plus 3x plus 3x squared plus x cubed, which you recognize, a Pascal's triangle. Okay, so the binomial theorem says that those coefficients are actually these choose coefficients. Okay, so just a reminder. This requires some proof. You can prove it by induction if you feel like it. So proof by induction. But anyway, I'm not gonna. You don't have to worry about it. I'm just gonna take this as a fact. Okay, so fact. Okay, so you've got this thing, the binomial theorem. And what we're gonna do is we're gonna play kind of a funny game, which is that we're gonna in what follows, we're going to try and control objects like this from below. Okay, we're gonna try to estimate from below things like this. Okay, and the way we'll do it is we'll say, well, look, this thing, like if we're looking at the size of this thing, that's equal to the size of this whole thing here, right? Well, no, actually. Where these guys are all, we'll be only dealing with x's when x's are positive. Okay, so if we're trying to get a bound on this from below, we say, well, this thing is equal to this thing, and then this thing is going to be bigger than or equal to some single term of it, right? So if we take like the first term of it, it's going to be bigger than or equal to 1, right? If we take, we could say maybe we only take the first 2 terms. But whatever, this thing is going to be bigger than than this thing if we throw out some terms. Okay. Okay. So anyway, you'll see what I'm talking about in a second. Okay. So now we've got enough to do the common limits that Rudin lays out. Okay. So here's the first one. The limit of 1 over n to the p as n goes to infinity is 0 for any p bigger than 0. right? So you've got 1 over n to the p. You know, p could be some tiny number, but no matter how tiny positive number it is, you know, 0.00001, as n gets big, this denominator is going to go to infinity, right? So you know that sort of makes intuitive sense to you, but let's prove it. Okay. So. So what do we want to show? Right? We want to show that, you know, given an epsilon greater than 0, we can find an n such that whenever you're past it, then 1 over n to the p is smaller than epsilon. Okay. Right? Everybody following? Right? This is just the definition, right? We want to show that given any epsilon, there's a time past which this thing is smaller than epsilon. Right? Okay. So as usual, there's going to be some scratch work. There's always some scratch work involved in doing these things. So you think, well, look, 1 over n to the p being smaller than epsilon, well, that's the same thing as saying that 1 over epsilon is smaller than n to the p. Right? I multiply both sides by n to the p, divide both sides by epsilon. Right? Both of those things are positive, so I'm not changing the inequality. Okay? Right? So, but that's the same thing as saying that n must be bigger than 1 over epsilon to the 1 over p. Right? If I take the p through to both sides. Right? So in order for this to happen, right? In order for this desired thing to happen, all I need is for n to be bigger than this. Right? So just choose any n bigger than that, right? Choose any capital N bigger than that, right? If n is bigger than that capital N, which is bigger than this thing, then this is bigger than that thing, and then you're done. Right? So you just say, well, look, so your scratch work is over. You say, choose any n that is bigger than 1 over, given epsilon, choose, given epsilon, choose any n that's bigger than 1 over epsilon to the 1 over p. Right? Then, if n is bigger than capital N, well, then n is certainly bigger than 1 over epsilon to the 1 over p, which means that epsilon to the 1 over p is bigger than 1 over n, which means that epsilon is bigger than n to the p. Which is what you wanted. Right? Everybody okay with that? Right? We just needed to show that here's 0, given some epsilon, right? These guys we wanted to show that we can make these guys as close to 0 as we want, right? We want to show that we can make them within epsilon of 0, right? We know that these guys are positive, right? So all we have to do is show that they're smaller than epsilon, right? We don't have to worry about this stuff down here, right? Because the things are all positive. So all we need to do is show that there's a time past which all these guys are smaller than epsilon, and we did that. It's okay? Okay. Okay. Okay, I'm gonna erase this. Is that okay? Okay. Okay, so common limit number 2. the limit of, as n goes to infinity, so you take some p bigger than 0, and you take p to the 1 over n. Okay, you take the nth root of p and let n go to infinity. Okay, what does that turn out to be? Does anybody know the answer? You take some positive number and you take higher and higher roots of it. You guys ever played with the square root on your calculator? No? Wait. You must have, right? No? Okay, I guess you guys had more entertaining childhoods, or less entertaining childhoods. If you take any number on a calculator, right, any positive number, 10, say, and you start taking square roots of it, square root, square root, what does it tend towards?
0? No.
It would tend towards 1, actually. Yeah, it would tend towards 1. Even if it's smaller than 1, but if it's smaller than 1, then we're taking square roots, then it gets bigger, right? And it'll head towards 1. So yeah, that's what stops it from going to 0, right? Because taking square root of a number smaller than 1 gives you a bigger number. Okay, so we're going to prove that. Right? So we want to show, as usual, right, given any epsilon, there exists an n such that if n is bigger than n, then p sub n minus 1 is p. Oh, actually, let me, just for simplicity, let me do the case p bigger than 1. So case p bigger than 1. Okay, so we want to show that that thing is going to be smaller than epsilon. Okay, so yeah. So yeah, let's see. What's let me see here. Yeah. So let's notate x sub n as this thing. Okay, right. We want to show that this x sub n. Want to show that x sub n goes to 0, right? Which is what we just said. Okay, and now here's where the binomial theorem comes in. So observe that 1 plus x sub n is p to the 1 over n, right? In other words, 1 plus x sub n to the n is p. Okay, now by the binomial theorem, this 1 plus x sub n to the n is this full blown thing, right? Right, n choose k, x to the k goes from 0 to n, right? But I'm not going to care about that. I'm going to throw out everything except for the constant and the first power term. Okay, so this is going to be 1 plus n x sub n. Right, that's the beginning. That's the beginning of your expansion, right? When you have 1 plus x cubed, it's 1 plus 3x plus blah, blah, blah. When you x to the 4th, it's 1 plus 4x, et cetera, right? Right. So let's just disregard everything except for the first two terms of the expansion. Okay. So, but this thing is P, right? So what do you see here? Why is this a good thing? We're trying to get control over x sub n, right? What we have here is an expression, saying that this thing is smaller, an expression involving x sub n bounded above, right? We have 1 plus nxn is less than or equal to p, right? I mean, it's actually strictly less than p. It doesn't matter, but it's true. Okay, so what does that tell you? That tells you that x sub n is controlled by p minus 1 over n. Right? Just subtract 1 from both sides and divide through by n. Right? And what am I going to say now? Right? We're trying to show that x sub n goes to 0. Why does x sub n go to 0? N?
Because 1 over n goes to 0, and
Yeah.
you can use like the product of,
Yeah. So we know that this guy goes to 0, right? This guy goes to 0, and we know that x sub n is this thing which is bigger than 0. Say. Okay. So this guy goes to 0. This guy's trapped between two things that go to 0 by the squeeze theorem. Squeeze theorem is what you need to invoke. By the squeeze theorem, this guy in the middle is going to go to 0 also. And so you're done. Okay. Yeah.
Wait,
sure.
sorry, why do we know that x sub n has to be bigger than 0?
Well, so p is bigger than 1.
Yeah.
And when you take a root of it, you're going to get something
Got
bigger
it,
than
okay.
1. Yeah. Right. The nth root, the nth p is bigger than 1, and so when you take the nth root of both sides, because this is an increasing function, it doesn't change the order of change the sign. Right. Whenever you have an increasing function, if one input is less than the other, then the outputs are less than, the corresponding outputs are less than. Right. So here are my inputs. 1 over n is an increasing function. Hey.
So from what I'm seeing right now,
Yes.
so first that you are trying to prove p over 1 over, there exists an n, like a natural number n, such that for any n, there is an n, then p of 1 over n minus 1 is less than epsilon. And you are trying to say that this problem is equivalent to the problem of trying to prove x of n approaching 0,
Yeah.
as you have proved here.
Yeah.
I just wonder why you didn't take the log immediately in from that original problem and claim that like the first integer greater than or equal to that log would be our n. Because you already assume that p is greater than 1. So I would say that the log function is monotonic at that point.
Yeah, I guess because we haven't introduced the log yet.
Oh, okay,
Yeah.
okay.
Yeah. So I mean, later on in the book, we'll actually define the log and stuff like that.
Oh,
But-
okay.
But yeah, so in this case, we're not. Yeah.
Okay.
Yeah. But yeah, that would certainly work.
Yeah,
Yeah.
okay. Because that move is like pretty new. Even if I haven't seen it before, I couldn't think about that move.
Does that mean you haven't read the book?
Yeah, I haven't. No, I read that, but like, I keep questioning like why they did that move
Yes.
because I forgot things and all of that.
Yeah. Yeah.
So I do math like pretty intuitively.
Yeah, no, this is it's pretty clever use of the binomial
Yeah.
theorem. And what you're going to see is that we're gonna milk the binomial theorem in the next two examples. Okay, so we're just gonna this is basically like a course, short course in using the binomial theorem. Okay, so here's another one. To show that the limit of n to the 1 over n as n goes to infinity is. Anybody know this one? This one's a little bit kookier, right? Because you're taking the nth root, but n itself is going to infinity, right? You may have seen this in calculus too, and the way you did it was probably by using L'Hopital's rule or something like that. But anyway, it turns out to be one. Okay, so we're going to play the same trick, similar trick. Right. We want to show that this thing minus 1 goes to 0. Okay. And so we play the same trick, notate, x sub n as this thing. Right? As before, 1 plus x sub n to the n is n. Okay, exactly the same trick as before, so far. Okay, now we pull out the binomial theorem, but look what happens if we try to play exactly the same trick. So this is certainly true, but it's not going to be useful. See what happens when we do this, right? What goes wrong? It's not really wrong, but why is this not helpful? Take 30 seconds and just imitate what we did before and see what happens. Okay, anybody see why that doesn't help you at all? What do we do? What do we do here? We're going to say what? What does this imply for us? Caitlin?
X of n
Mm-hmm.
is equal to n minus 1 over n.
Yeah, I'm sorry, this should be a less than. But is less than or equal to what?
N minus 1 over n.
N minus 1 over n, yeah, right? And then as n goes to infinity, what happens? This goes to 1. We get that x of n is smaller than 1. But that's not what we want, right? We want x of n to go to 0, right? All we have is just that gives us a bound, but it doesn't give us the bound that we want. Okay, so that maybe you try it, but it doesn't work. Okay. Okay, but you can take the second term. So instead, use the x squared term from the binomial theorem, right? So that's going to be n choose 2 x of n squared, right? So that is right, n over 2 factorial, n factorial over 2 factorial, n minus 2 factorial, right? So that's going to be, that's just going to be n times n minus 1 over 2 times x squared. Oops, That won't work. Okay, so instead of taking the 0th and the first term, we're going to use the second term. Okay. So, use the second term. Right, so we get n minus 1 over 2, x n squared is less than or equal to n. Right, so right, instead of using these guys, we're going to use the term right after. Okay, and then what we get is that that x of n is smaller than 2 over n minus 1. Xn squared is smaller than 2 to the n minus 1. 2 over n minus 1, right? And then as n goes to infinity, xn squared is going to go to 0. And so x is going to go to 0. Okay. Okay, let me do the, is that all right? Okay, so basically the last example is the following. This one is in the list of common sequences, but I don't know if I would call this a common sequence. I think this is not really a common sequence. It's rather a chance for Rudin to pull more out of the binomial theorem. Okay, so here's the thing, right? So, whoops. Wants to show that limit is 0. That this thing goes to 0 for p for any p bigger than 0. Okay. So right, what this is saying, look at it, right? So you've got n to some power on the top, right? Like n to a billion, n to the billionth power, right? And you've got some number bigger than 1 on the bottom to the nth power. So right, so you've got n to the 100, say, and you've got 1.01 to the n on the bottom, right? And what this is saying is that, this is basically saying that having the n in the exponent is going to beat out having n in the base, no matter how big the exponent, no matter how big the fixed exponent is. Right? You've got n as a base to some huge exponent. You've got some tiny number, but bigger than 1 to the nth power, and this is going to go to 0 no matter how big this number or no matter how small this number. Okay. So it's like a racing, it's a speed competition basically, and exponent wins over base as what you would expect. Okay. So the proof of this is cool. You say, well, look, we've got. We know that this is going to be equal to, right, summation n choose k, p to the k from 0 to n, right? So, right, so that is going to be, that's certainly true. And that's going to be bigger than any single term. Okay. So if we take any one of those terms, this is certainly true. Okay. So now, well, this being bigger than that means that, of course, the reciprocal is smaller than the reciprocal. Right, which is going to be which is, sorry, k factorial and n minus 1, n minus 2, n minus k plus 1 over p to k. Right? Right. Remember, n choose k is n factorial over k factorial, n minus k, n minus k factorial. Right. So all I've done here is just when I take the reciprocal, I'm putting the k factorial on the top, and then I'm doing some cancellation here. Okay, so let's come back over here. We're going to use this to get control over this thing. So consider n to the alpha over 1 plus p to the n. Well, that's smaller than n to the alpha k factorial over n minus 1, n minus k plus 1. P to the k. Okay, so now what we're going to do is we'll say let k be the greatest integer smaller than alpha plus 1. So alpha, alpha is some real number, right? So take the greatest integer, the greatest integer is smaller than alpha, right? So like, if alpha is 1.1, then the greatest integer is going to be 1, right? It just chops off the decimal portion, basically. Okay. Except for negative numbers, and you just assume it's positive. Okay. So and then for n bigger than 2k, for n bigger than 2k, sorry, got missing. For n bigger than 2k, each of the terms on the bottom is bigger than n over 2. Right? Because n is bigger than 2k, right? And we're basically subtracting down. We're subtracting down to k, right? So each of these things is going to be bigger than n over 2. Does that make sense? Right? N is bigger than n is bigger than 2k, and when we subtract off things, here we're taking n subtract 0. We're taking n minus 1. We're taking n minus k minus 1. Right? So the most we're subtracting off is something smaller than k. Right? The most we're subtracting off is something smaller than k, and n is bigger than 2k. Right? So here's 2k. N is bigger than it, and we subtract off. We subtract off at most k minus 1, right? We subtract off at most k minus 1, so we're bigger than, we're going to be bigger than n over 2, right? Okay, I hope that makes sense. So each of those terms is bigger than n over 2, right? And there are k of them, and there are k of them. Okay. Right. So what does that mean? Each of those terms is bigger than n over 2. So that means that this whole thing is smaller than, n alpha k factorial over n over 2 to the k, p to the k. Right? Because each of those guys is bigger than n over 2. So thing is smaller than 1 over n over 2 to the k. Right? Which is the same thing as 2 to the k, n to the alpha minus k, k factorial over p to the k. Okay, but k is bigger than alpha, right? K is bigger than alpha because k is the greatest integer smaller than alpha plus 1, right? So it's going to be the integer just bigger than alpha, right? So we have alpha minus k, that's a negative power, right? So we've got, right? So what do we have? We have that that this guy is controlled by some constant times something times n to a negative power, and when you raise n to that, when n goes to infinity, then that goes to 0. So that goes to 0. So again, by the squeeze theorem, we get it. Does that make sense? I think, maybe I didn't do too good a job.
That choice of k is, I think the author had to reach that point and then choose k before Rudin choosing k. Because that choice of k is like,
Out of nowhere, maybe.
yeah, you need some information.
Yeah. So why do we choose this k? In order to make this succeed. Yeah. And you could choose, you could choose a k that's much bigger than, than alpha. This is sort of like the minimal one that will work, right? So yeah, but you do need to choose something like this, like n bigger than twice k, in order to make this fraction work. I mean, you could do something different, right? Right. If you choose n bigger than 3k, then subtracting off, then it'll be bigger than 2/3 n, right? Whatever. So yeah, but I hope you guys see what's going on, right? You choose as n gets really big, it's going to be bigger than 2k eventually, right? And so once that happens, then all of these terms become bigger than n over 2, right? And then you get this thing to pull out. Okay. Let me just say that there's one consequence here. So there's one final common sequence that Rudin mentions, and it is that the limit of x to the n is 0 as n goes to infinity for x of absolute value less than 1. Okay, and let me just show it quickly for. Let's do it for x positive. Okay, so right. So let's do it for x positive. If x is smaller than 1 and greater than 0, then then x can be written as 1 over 1 plus p, right, for some positive p. Right, right? Okay. Okay. But then you just invoke the previous one. So invoke 4 with alpha being 0. Right? That says that the limit of 1 over 1 plus p to the n is 0 as n goes to infinity. Right? But that's the limit of x to the n is infinity. Okay, that's it. That's it for today. See you guys next time. Okay, so yeah, next time we'll get into these things called Cauchy sequences, which are extremely important.